All right, guys, today we got inferences from two samples again. Still working with two samples, but today instead of doing two proportions, we're doing two means and two means from independent samples. We'll get to what that is in just a second. Again, independent samples, we're going to assume a couple of things. We're going to assume that we do not know the population standard deviation of either sample, and we're also going to assume that the population standard deviations are not equal. If they're equal, then that changes things. We're going to assume that they're not equal, and also that we do not know what they are. All right, a couple definitions here. Two samples are independent. Big word today, independent, if the sample values selected from one population are not related to or paired with or matched with sample values from the other population. Dependent is just the opposite. The sample values are paired. That is, each pair of sample values consists of two measurements from the same subject, before after stuff, husband-wife data, where the matching is some kind of relationship. All right, an example of each one. Independent would be this. It says researchers investigated the reliability of test assessment. One group consisted of 30 students who took a proctored test. Another group consisted of 32 who took online tests without a proctor. So those two samples are independent because they're not paired or matched up in any way. Okay, dependent would look like this. Students of the author collected data consisting of heights of husbands and the heights of their wives, and their findings are listed below. This is dependent because they're matched in a certain way. Each husband is matched with their wife, so they're matched or paired together in a certain way, which means it is dependent. Notation, you should be familiar with all these by now. Mu, population mean, standard deviation, population, sample size, sample mean, x bar, sample standard deviation, and of course if we change them to twos, it goes for the second sample. So all those are same ones we did last week, except we had p here instead of mu. That's mainly the only difference. So you should know those notations great by now. Requirements, and again, your book does a great job teaching your requirements, but then it gives you problems. You don't have to worry about them anymore because they only give you problems where requirements are met, but you do need to know what they are. And here they are. Again, we do not know what their standard deviations are for the population, and we assume that they are not equal. They have to be independent of each other, which we talked about a second ago. They both come from simple random samples. That's always a criteria. Either or both of these must be satisfied. This won't surprise you. The sample sizes are both over 30, or they come from populations having a normal distribution, because we're dealing with means, which is always the case when you're dealing with means. All right, hypothesis test. Here's our t-test, and it's a t-test because we're using means like we have all year. It's crazy how it all kind of comes together. It's a t-test, and it's a different formula because it's a two-sample test, so we have to change. Now, we are assuming in our hoe all the time that M1 or mu1 and mu2 are going to be equal, so that parentheses right there will be 0 all the time. So really you can look at this right here as your test stat, and it's t distribution because it's mean. Normal distribution like we did last week for proportions, t distributions for means always. Hypothesis test. Test stat for the two means has degrees of freedom. We're going to do n-1 again, whichever one is smaller, either the first sample size -1 or the second sample size -1. Whichever one is smaller, that's going to be our degrees of freedom. P-values we're going to get from, not from the table, but from technology. Critical values also from technology. You're welcome. Okay, confidence interval. We're also going to do, just like we did with proportions from two samples, we're going to do the same thing with means. So we're going to do a confidence interval. And the way you do that, you got to find E, and you add it to the difference and subtract it from the difference of your two sample means. So here's how you're going to find E. Except to be honest, I think we can do this with technology also, but if we do it by hand, that's the formula we're going to use. And again, degrees of freedom is the smaller of sample size 1 minus 1 or sample size 2 minus 1. Okay, let's do an example real quick, or slow. I'm having a hard time with that word today. Researchers conducted trials to investigate the effects of color on creativity. Subjects with a red background were asked to think of creative uses for a brick. Other subjects with a blue background were given the exact same task. Responses were given by a panel of judges. Okay, researchers made the claim that the blue enhances performance on a creative task. Now, the blue is actually our second group. So N2 or X bar 2, that's going to be our claim. Okay, test the claim using a .01 significance level. Okay, requirements, take them real quick. And I know they're going to work because it's your book. The values of two populations are not, we don't know those. Are they independent? Yes, they're not related at all. One's doing blue, one's doing red background. Are they're random samples, and both groups had more than 30, so we're good to go. All right, here's the data we found. Once they did the gather the data, this is what they found: the red group here, the blue group here. Those are the numbers that they found. The means fairly close. Like, not really though, because it's only 3 into 3, so it's really kind of split apart. Standard deviations are fairly set apart too. Okay, the claim that blue enhances. Remember, the claim the blue is the second group. Blue enhances performance. So if that's the case, we would say this. We would say, okay, that means the second mu would be greater than the first mu. And that's how we're going to kind of write it here. So let me go to the next slide. So just like we did proportions, this is always going to be our hoe. Mu from sample 1 or population 1 is equal. That's always going to be it. We're going to assume that the two means are equal to two mu's are equal. Now, because we said where the claim is that the blue enhanced, we're expecting the red to be less than the blue. So that's how I'm going to write that there, less than, and the sig level is 0.05. And because we're doing mu's, we're going to use a t-distribution, All right, calculate the test stat. There's our formula we had earlier. I plugged in all the numbers right there, punched it in my calculator, and got that for my t-stat. Okay, negative 2.979. That's my test statistic. Let's see how it compares with what the t-stat is. Okay, there's the picture. There's my critical value. My critical value is negative 2.441. Our test stat we found on the last slide was negative 2.979, which means it is in the rejection zone. I used 34 degrees of freedom because one sample size was 35. That was the smallest sample size. So, and your calculator will take care of that for you. But anyway, the test stat is in the rejection zone, so you know what that means. That means we can reject the null. And if we reject the null, n minus 1 that are equal. Also, when we do p's in a second, the p-value, if you did find it, was this right here, 0.0021, which is less than 0.01. Remember, the p-value method and the test statistic or the critical value method always give you the same answer. Okay, so what we would say then, because we're rejecting the null and the claim was the alternative, we'd say there's sufficient evidence to support the claim that the red group has a lower mean creativity score than the blue background group. Good night. All right, so just what we expected. Okay. Last thing here, using the data from this color creativity example, construct a 98% confidence interval estimate for the difference between the mean creativity score for those with the red background and mean creativity score for those with the blue background. Okay, so now we're going to do the same thing, except we're going to do a confidence interval, 98% confidence interval. So here we go. First thing I do is I got to find E, what my error is, and did that all the way through there and found my error right there, 0.475261. And don't forget, this is our x1 and x2. So what you do is you subtract your x bars, and you're going to subtract E from that, and you're also going to add E to that. And this is what I get. And right now from doing proportions, at least I hope I was expecting my 0 to fall in there. And because they're both negative 1.06 and negative 0.10, 0 is not included in there. And because it is not, we can say this: we are 90% confidence that the limits of this actually do contain the difference between the population means, which means because they don't include 0, that means there's no significant difference between the two means. So basically you can reject HO because we did not get 0, and we can say that there is a difference between the two means, some kind of significant difference. Hope that makes sense. Guys, this is really the same thing we were doing with proportions, except we're doing t-distribution because we're doing means, and a couple other very small differences. You calculate E differently, but we're going to use technology a lot anyway. But really the same type stuff, and I hope you get that. I hope it kind of coming together for you, and I'll see you in class tomorrow.